Hello, everyone. Welcome to the Friday seminar. So it's my pleasure to introduce Dr. Yimin Yang. Yimin is currently a tenure-track assistant professor at Computer Science Department in Lakehead University, and also he's a faculty affiliate of the Vector Institute. He got his PhD in pattern recognition intelligent systems from Hunan University in China in 2013, and afterwards he has been a postdoctoral fellow from 2014 to 18 at University of Windsor. His research interests are in machine learning, neural networks, and signal processing. He's authored many papers, 50 journal papers, and also is an associate editor of IEEE Transaction of Circuits and Systems for Video Technology and Journal of Neurocomputing. And so please join me in welcoming Yimin to this talk, to Friday seminar series, and
Thank you, Dr. Fahamed. Okay, let me share my screen. Yes. Okay. Hello, everyone. Good morning. Thank you so much.
Sorry, before you start, Yimin, just the thing that we had before where we can see your next slide.
Still can see my next. Okay.
Yes.
Now?
There we go. Yes, perfect.
Okay.
Thank you.
Okay, so hello, everyone. It's my great honor to have this great opportunity to make my research talk here. So today I'm going to discuss about my research area, actually, in the machine learning methodology. So during the past 10 years, or even maybe 15 years, I mainly focus on the machine learning methodology, especially for using a non-iterative learning strategy for training neural networks, no matter it's a shadow network or deep networks. So today, the title of this talk is Artificial Neural Networks with Non-iterative Learning from Single Layer Network to Hierarchical Networks. Okay, so for this talk, I mainly can divide this talk for three parts. The first part is how to use a non-iterative learning strategy to train a single layer network, because we all know before maybe 10 years ago, or even 20 years ago, we almost use single layer network, no matter it's RBF network, SVM, or random forest, or any other networks, okay? So this is my initial work when I was a PhD student, and I also want to introduce why I'm moving to machine learning area. So the second part is about how to use this kind of non-iterative strategy for training a hierarchical networks. Many focus on fully connected networks, even as like a multi-layer network with fully connected networks. And I'm moving to deep learning very late in 2018. So I moved into deep networks. So the last part is my recent works in this area. So let's start one by one. So first of all, I would like to discuss why I'm moving to machine learning area. I know there are a lot of postdoctoral PhD students and also researchers in this area. So I would like to share my experience or my research journey why I'm moving to this area. So all are starting from a very small idea. So when I was a PhD student in 2009, so actually I was grew up from pure engineering. My bachelor's degree, master's degree, PhD degree all come from computer science, even electrical engineering. So in my lab, most of the people focus on robotics. So we have very big funding supported by the government, is that we have very heavy winter storms. So in maybe 13 years ago. So many people has been died while moving the snow and ice from the power line. So we have some demands from the government that we need to build a robotic system. So those robotics will be using for de-icing robots. So when we are trying to develop robots, the main problem is that how to learn the dynamic system of the robotics, especially the robotics are running in a very uncertainty environment. Like here, the robotics will moving on the power line. So, however, I am not a robotics guy. I have no knowledge about the mechanics or the mechatronics background. So one day my supervisor approached me saying, "Hi, how about find a neural network for the identify robotics dynamic system, but I don't want a high performances, but I would like to have a fast learning speed. So then the robotics could be the neural network itself can learn the dynamic systems online without any other pre-knowledge. So this is the real demands from the industry level. So as a year one PhD student, I have no idea about this. So I approached into a journal. At that age, I believe this is the top one journal in the world in neural networks. So it's TN. So I searched the journal sorted by time cited. So during the past 5 years, what is the hottest algorithms published in this journal? So at that moment, I found this one. This is the top two. The number one is a survey paper. So I choose to read number 2 first. So the paper is universal optimization using incremental constructive feed-forward network with rounded neurons. So why I started to read this paper is that this paper tells us algorithms called extreme learning machine. So in that age, because this paper published in 15 years ago, so in that age, many researchers are focused on single-layer network. So in that age, of course, the most important part is a supportive machine, random forest, or some other network. So the performance actually is quite similar. I think I conducted this experiment several years ago with my MATLAB. So I try to show you guys why I try to use this better. So for example, this is protein datasets, classification datasets from the UCI dataset library, quite small datasets. So the performance is quite stable, no matter you pick random forest or supported machine, any other classifiers. So the ELM method could provide a significant difference in terms of training time. It almost can, improve your training speed up to thousands of times. And back to 15 years ago, there's no GPU. So everyone focused on CPU with RAM, with memory, right? So this is what I need. So I using this method, and it gave me a very good result in the robotics area. So after take 1 year in that area, I feel why not moving my research focus on pure machine learning. So then this is my first job in this area. So firstly, let me just briefly introduce why the original extreme machine looks very fast. So in a single layer network, traditionally we have input weights, BELs, and output weights. Even nowadays, we only focus on input weights and BELs because the network is deep. We have 100 layers, so each layer we have only input weights and BELs. So the output weight has been gradually removed. But back to 15 years ago, we still have those 3 parameters. So X is our input data. A is the input weights, B is the BELs. We have an activation function. In that age, maybe sigma, sine, cosine, RBF network, no matter what it is. So we have an output weight called beta. So we definitely need to use SGC method using backpropagation to train this network multiple times or even hundreds of times. We call tuning parameters. I know everyone is quite familiar with it. So the ELM using a random generation instead of a computated weights. So that means the input weights and the BELs are random generated. So because this 2 part of parameters has been random generated, so you don't need to take time to tune the parameters. So for the output weights, they use a MP inverse matrix to solve these equations. So only use, you can see here, G is the activation function, X times A plus B. So this is the actual output from here, right? From here, actual output from here. So with the design output T, with a MP inverse matrix, then we can get the trended output weights beta. So in here, A, B are matrix, beta is vector. So using this equation with one time, then you can terminate the process. That means no iterative learning strategy has been involved here. So that is the reason why it looks so fast. And surprisingly, the performance is also okay, and at least at that age, because in that age, everyone use UCI data sets, quite small, and at least maybe you can try MNIST. That is maybe the biggest one, to my knowledge. So I feel at that moment, I feel that, so right now, the A, B are random generated. Why not pull the arrow back to retrain the A and B? Because if A, B could be randomly generated, if we retrain these two parameters, definitely it will be work. But I don't know the performance is stable or not. So I try to do this one. A very simple one is that try to pull the arrow. Right now, I already get the arrow. So I try to update the arrow, pull the arrow back through the activation function, and then retrain this one. So when we try to pull the arrow back and also retrain these parameters, we still use the MP inverse matrix, not the SGD method. So with this, 1, 2, 3, done, no iterations. So this is the moment I feel I really want to move into the machine learning area because it's very, very interesting. It's not just interesting. Like I can talk to you guys. If you're working in the robotics area, you need a lot of support. But if you're working in the machine learning area, you basically at that particular age, you don't need too much support because the data is real. If the data is real, you will get the real result. But in robotics, you need a robotics body. But most people will using a MATLAB to simulation to get a simulation result, right? But in machine learning, we will get the real result as long as the data is real. So the blue curve is the proposed method. Others are the ELM-based method. So these two data sets is also very small, all come from the UCI datasets library. So of course, when we increase our hidden neurons, the performance will be increased. And as well, the testing error will be decreased. So you can see here when the number of neurons increased, the testing error has been decreased. But for us, only with 2 neurons or 3 neurons, it can reach to the limitation of these performances. I would say all those limitation performances are quite similar because it is just a single layer network, right? But with only several neurons, it can push to the limitation of its performances. So this is the real, maybe the most important and impressive moment I have till now. So then I can test a lot of data sets. So I named this one as a bidirectional EOM because I would like to use these algorithms to train both input weights and output weights. So it's like a bidirection. So I name it as a bidirectional external machine, only focus on regression problem. So compare with the original EOM method, in the regression data sets, it will be reduced up to 400 times in terms of required neurons. The performance is stable, maybe a little bit better, 3%, 1 to 3%. And the training time could be further improved up to 250 times. So this result actually motivated me to moving forward. Okay. So then let's move to the second part of this work. So when I moved into Canada as a postdoctor, especially in 2013 when I finished my PhD, at that particular age, most of the people in this area focus on multi-layer network or hierarchical networks. I read Dr. Jeff Hayden's paper, which published in Science. It's quite late. I read that paper in 2014. Even he published in 2006 in Science. So, and that based on that one, I feel why not extension this idea from a single layer network to hierarchical networks. So, and that particular age, what we can see is that we already have this bidirectional EM method. So why not extension the idea to a two-layer network and finally to the hierarchical networks. So because of this, we will have more wide industry application, like as any CV tasks, it could be used, right? But in terms of machine learning methodology, I would like to use a non-iterative learning algorithms to replace or to, how to say, make some modification. So I want propose such hierarchical networks with non-iterative learning methods. Okay, so right now, what I had in this and that moment is I have this bidirectional EOM, we call BEOM. But I can finish the training with milliseconds in my CPU. So why not extend this structure from a single network to a lot of networks? So it's like I have network one. So in this case, I introduce another network. This is network two. And I can introduce n networks because each network I could finish the training within milliseconds. So I still do not need to wait too much time to get my single result. So it's like you build a row by yourself, a concrete row. So it's tough. So now you have some workers and we can working together to build the same row. So it's much faster, it's easier. And unfortunately, because we have to hire any worker, the budget is limited because we can finish the training with milliseconds. So that means we have such resources to do so. So in terms of methodology, you can see here, we use E to represent the error. So of course, our idea is that the E equals to 0. So first we try to using the method to approaching the designed output T. So I can use the pen. So this is our target. So O1 is the actual output from the network one. So when we finish the training, we try to update the error. So E is our new target. So then we will design another network. So this network output and the network one plus together to approaching the design output. And we can do multiple times till approaching the result. Okay, so I know most of the audience will worry about the overfitting problem. I will discuss later. So this is the algorithm part. In the network architecture part, it's like this is the single network. So now we will have n neurons. Each neuron itself is a single layer network, right? So in this case, for example, if we use 10 networks, so we will have 10 neurons. Each neuron itself is a single layer network. So I name this one as a subnetwork hidden neuron. So this is the step one, what I did. So in terms of the algorithm level, so now this is the original extreme machine. The neuron has been random generated with this bidirectional EOM, or the neuron has been calculated with NP inverse matrix. So we will have a bidirectional EOM. Then we want to extension this idea from a single layer network to hierarchical network. So what we did is we also get a target. So we try to use these equations to update the hidden layers here. So once we finish this one, we still want to pull the arrow back through this layer. So we will try to get the designed output for this layer. Okay, so for example, I have an input, designed output and actual output. I will use the design output to update the weights here. So once we finish this one, we want to update the current arrow. So this is the current arrow has been updated only based on the adjustment of here. So once we did this one, we fix these parameters and we update the arrow. And then we pull the arrow back through this activation function. When we pull the arrow back, we still can use the MP inverse matrix. So once we do that, we will get this one. The capital P represents the designed output of here. So now I have input, I have designed output. Then we can still use the same strategy to train the parameters here. So once we've done this part, terminate the process, no iterations. So in this case, we can see there's no learning rate, no learning momentum, no learning required epochs. So this is the level of accuracy. So later on, this is what I did, is that I try to extension this single layer network to a two-layer network structure. So there are still several differences. For example, in the fully connected layers, actually those layers should be connected. But based on this kind of network structure, this two neuron is disconnected. So they're only connected between this. And then finally, we can extension this structure to a multi-layer network within subtype neurons. And then try to transfer this idea to your hierarchical networks. So in the hierarchical networks, there are three general layers, which I decide. The first one is try to extract features. Second one is try to using feature combination. And finally, we use like softmax to get the final result. So for this hierarchical network, actually, it will have 100 million or even 200 million neurons inside. But because we use such non-iterative learning algorithms without any learning epochs, so we still can using CPU to train the network. And it's just several seconds, we could get the result. Okay, so let's just summarize the performances. So compare with these hierarchical networks, we can further improve the performances in both classification problem and the regression problem. So it's about, even we use multiple hidden layers, the required neuron actually itself has been reduced. It is quite surprised. Classification problem, classification accuracy improved up to 17%, and the training speed can even up to speed up to 200%, 200 times. So for regression problem, we will have the similar result. And then this is the age of deep learning. So just to talk about the computer vision task. So there's three well-known data sets. I think it well known for everyone in this talk. So for the C15, which is very small data sets, so the human recognition level is 95%. With this kind of learning algorithms, we can get 98.2%. And for the deep network like AlexNet, VGG, GoogleNet, ResNet, is around 90%. So for CASIC 256 and CASIC 101, the performances is also a little bit better than others. But it is not the entire picture. This kind of structures is very useful for small data sets and medium data sets, but the performance in the ImageNet is not good. It's not good. And so that is the challenge. So let me just summarize the differences between this so-called hierarchical networks with deep convolutional networks. So there are several advantages. Of course, there are also several big disadvantages. So for the parameters, the current SGD-based method in convolution network, we need to use the learning rate, learning momentum, bench size, and others. So in this case, there's no. We have only one, which is L2 recursion coefficient. And this parameter is super unsensitive. That means the performance is quite stable. So this is the advantage way. However, the disadvantage way here is that the SGD-based DCM model, we will have much better performances, especially in computer vision tasks like ImageNet. We will have used the CPU-based computation resources in the SGD-based DCM model, and it will have more parameters, and of course, it requires more training time. So especially nowadays, we have multiple GPUs, and I think for every researchers, we desperately need more GPUs, right? We need more graph card to conduct our research, and we have to wait so many days or so many hours to get a single result. So I still very, missing the moment back to 10 years, and that moment with such method, we have no parameters. That means you don't need to tune in your parameters, right? So nowadays, we have to facing such challenges. So in the MP inverse matrix, this method, it have more learning speed and has acceptable performances in tabular data or small image data sets. So tabular data means like EEG data sets, bioinformatic data sets. Those algorithms works very well, and it's much faster, so you can conduct those results in CPU. And another phenomenon I suspect is that it looks like the overfitting problem is a little bit smaller. So, but I'm not quite sure, so I highlight this part. Okay, so then let's move to the last part. So the last part is deep network. Of course, this is the age of deep learning. So we all embrace such great technology. So historically, we have very interesting circles, like Rosenberg proposed perception in 1950s, and it sent to Winter in 1970s. In 1970s, we have hop-forward network, and in 1990s, we will have we had a support vector machine and RBF network. So nowadays, we're using deep network. So deep network become very famous and already dominant this area. If you don't use deep convolutional networks for computer vision tasks, it will be very surprised and weird at this particular stages. So it became very famous since 2012. So this size actually is very familiar for all you guys, but I want to express my idea and also the concern. So since we have ImageNet, so the deep networks make a tremendous progress. From AlexNet to NASNet, or even nowadays, we have a GBT modems. So the performances on ImageNet has been significantly improved. But you can take a look at this. So in AlexNet, the performance is 57.1 with only 8 layers. So VGG has 16 or 19 layers, and it can approach into 70%. So ResNet with 50 layers has 77%, and nowadays NASNet has more than 1,200 layers in my lab. The performance is 81%. You can see here, this is a big jump from 8 layers to 50 layers, or even from 8 layers to 100 layers. It's a big jump in terms of performances. But when you increase the layers, we already reached the limitation. I know there's a lot of algorithms. Right now, we are using different loss functions to further improve performances. But my concern is that as a graduate student, as a PhD student, even as postdoctor, how you can survive in this gradient tendency. We were waiting so many days to get a single result. And with different learning rate and different parameters, maybe the result has been changed. So it's less confident to propose your method and say, my method has a great performance. Because with different combinations, you two will have different result. And want to get the single result, it takes several hours. So my dream, I know it's a long dream. So my dream is try to introduce such non-iterative learning strategy to deep networks. I know it's taken a lot of time. I believe maybe 10 years or even 20 years. So what I have done right now is that, so in 2018, I feel maybe it works very well. So what I can do is that for any convolutional networks, no matter it's RASNet, DenseNet, or VGG network, we can separate this network to two parts. The first part is convolution part, and the second part is the fully connected parts. So for the convolution part, we will have max pooling, ReLU, and some others. And for the fully connected parts, we will have dropout, ReLU, and a fully connected network, right? So step by step, my understanding is that how to introduce this non-iterative learning method to this fully connected parts, try to retrain it, because I cannot find a way to train the entire programs, to train the entire network. It takes time, and we don't have such strong support. Like you need to use CAN or CUDA, C++ language to write a basic code to wrap up a library first, then using such library to support your research. So it's taken years. But what I can do is that, how about retraining this network by using such proposed method? So this is a paper. I conduct this research for almost 3 years. And to be very honest, 2.5 years, I just want to get my result. So, right, half a year propose the method, writing the code, and waiting 2.5 years to get a single result done. So my strategy is like this. For example, I use 3 fully connected layers. So I use VGG network. So what I can do is that for VG16, we have 3 fully connected networks, layers. So layer 1, layer 2, layer 3. So first we try to get the actual output. Then we will have a designed output. So we will get an arrow. So as the same, we try to replace this arrow. So the arrow will be traced back from the layer 1, layer 2, and layer 3. So firstly, we try to get this designed output P. So P is the same as the designed output of the hidden layer. So using such method, we will try to update the weights in the last FC layer. Then we will, using this equation, to pull the arrow through the ReLU layer and the dropout layer. Then we will fix the design output for the new fully connected layer, and using the same strategy to update the weights. So here we introduce learning rate, because learning rate in this particular data set, in this network, is very important. So learning rate is important. So previously we never use learning rate, but here I have to use learning rate. So for example, here, this is a Cypher 10 datasets with red AlexNet. This is the original SGD-based master with learning rate. This one is our master retrained with learning rate. And the green curve is without learning rate. You can see without learning rate, the performance has been dropped along with training epoch. And in terms of performances, there are several results. For example, in CIFAR 10, I use AlexNet, VGGNet, GoogleNet, DanceNet, ResNet. So the performances based on the traditional SGD method, I use SGDM. So this is the area covered. So with the recomputation strategy, this is the covered area. So for each network, we have some improvement in terms of performances. And for big data sets like Palace 265, so I use transfer learning. So the model was trained by ImageNet because I want to improve I don't want to wait too much times. So that's the reason you can see here that with only 6 training epochs, the performance improved a lot because the result comes from the trans-learning network. So this one is our proposed method, and this one is the SGDM-based method. Okay, we also try to improve. But sadly, you can see this is the performances when we have 500 training samples per class. And this one is 1,500 training samples per class. That means I increase the size of the network, the size of the data set. The performances, the gap of these performances has been decreased. So yes, so even it is not my expectation, but this is the truth and what I get. So then take a look at this table. So this table, we're using those median data sets. And the result is from AlexNet, VGG, DanceNet, also ResNet. So from AlexNet to VGG, you can see here, the layer has been improved, has been increased, and the number of training parameters has been increased. So we will have a huge jump in terms of performances improvement. So around 15% of the accuracy improvement. So for GoogleNet and for ResNet. So from GoogleNet to ResNet, the performances actually has been only improved to 2% or 2.7%. For our proposed method, you can see here, even without any network, additional network, like we still keep the same network size, sometimes we can improve 0.5%, sometimes we can improve 2.3%. So 2.3% is not huge, but if you consider what we can get if we keep the same SGD-based method, we have to improve, we have to increase maybe 3 times of the network size to get such a gap down. And another reason is that is the training time. So in the training time, we use a 1080 Ti. So this is the training time per epoch when we try to use SGD method. This is the feature extraction time, because for the current method, I cannot build in the deep side. That means I cannot wrap up all those proposed methods and put into the Keras or TensorFlow. So what I need to do is that first I want to get the feature. I want to extract the features. So that try to get the features, it take roughly 100 seconds. But for computation with my proposed method, it's just a 6 second, 1 second, 1 second, 1 second. And all those has been done with CPU, not GPU. So I believe if we can implement this algorithm to GPU, it will be much, much faster than this. So one of my co-supervised PhD students done this job is he tried to introduce learning momentum. So the previous way you introduce learning rate. So he introduced learning momentum, and then he tested the performances. So for CASIC 256, you can see here, all those are SGD-based method, and this is the performances. And with this method, we can get much high performances with fast learning speed. Like for example here, with only one learning epoch, it almost can finish the training. Okay, so this is the advantages. Then let's talk about disadvantages. The disadvantages is what's next. So you can see here, the motivation is quite clear. Of course, right now, what we can do in this PAMI paper is we try to retrain some layers, of course, in FC layer, fully connect layers. We can do this. How about using the strategy for entire network training? So right now, during this pandemic, I would say, I got some result and some disadvantage result. So what I can confirm is that using the retraining structure, as mentioned in this PAMI paper, we can have some performance improvement. But what we want is that we want less tuning, less required computation resources, like we can conduct this examples or experiment in CPU, not GPU. And we want higher performances. So this is a major advantage I want to get, but I don't know. I really don't know whether I can get it or not, because it takes time. So the challenge why I cannot ensure is that there is no function supported from Keras, TensorFlow, Multilayer, CUDA. All those functions library should be manually coded with C++ CUDA. So, it's taken a lot of time. And this is for the tough job. So second one is how to pull the arrow through the max pooling. Because in the convolution part, the arrow should be pulled through the max pooling, or even some orders. I know there are a lot of layers, not just convolution layer. There are ReLU layer, max pooling, and so on. So this is also we need to know. But to be very friendly, I don't know how to use mathematics to prove it. I don't know. But what I can do is that I want to get the code down and get the result down and compare the result with different combination parameters. So there's another several open questions like loss functions. So in all those, my paper, I use softmax. How about all the loss functions? I know there are a lot of loss functions, especially right now we have some very good loss function in safe learning area. So then, how about in these three conditions, transfer learning, training from scratch, and safe learning? So those all are open questions. So here I would like to encourage you guys to join this area because this is a high risk but high reward area. Okay. Yes. So this is my research talk, and all those paper listed here, the code are available in my homepage. So if you guys have interesting, you can find the code. But most of the code are written by Multilayer because I come from engineering part, and some code has been done with Keras or Python by my graduate students. Okay, thank you.
Great, thank you very much. Very interesting talk. So I think we have time for questions. Please, audience, please ask questions if you have any. So maybe I start with asking a question about say, neural networks that are like recurrent neural networks. Have you thought about whether these ideas can be used in that context, that we have some kind of recurrency? Because I think similar to extreme learning machine, there is this echo network, echo state machines, which are essentially, I think, the recurrent version of it. Is there kind of equivalent of bidirectional echo network machines that you have worked on?
Oh yeah, it's a very good idea. I never use this method because for ELM, like extreme machine and echo state network, actually is quite similar. All are belong to the randomized network family. One for ELM is for feed-forward network, and the echo state network is for recurrent network. I didn't use this idea for recurrent network, but I believe it still works. But there's a big differences. Is even I use the type of extreme learning machine, but for me or for those algorithms, all those neurons has been trained, but not rather than random generated. So I feel some very important result is that if you have a small data set or medium data set, single line network with random neuron works. But if you have conduct like Cypher10, this vision tasks, random generation neurons, it will be, reduce the performances. But for this one, because right now we can deal with NLP in this area and tags or those others. So those paper or those algorithms, I believe it could be used for a single classifier, but we need a feature extraction method, like vector, word to vector, or those feature extraction method. If we can combine with these classifiers. Maybe we can get a fast loading speed, and at least we can have more easy result can be obtained. And I know there's a lot of, waiting a lot of time and to get such a result.
Okay, thank you. So I think there are other questions. There is one question in chat. Vino, do you want to ask a question?
Yes.
So maybe I read the question. So the question is that, do you have any future plan to release this algorithm as a package?
Yes. This is my painful point, to be very honest. So right now I have several students. They are trying to release those. So what we can do is that first we have to fully manually coding these algorithms in C++ CUDA code. So once we get the job done, so we will try to transfer this code to multiple versions for MATLAB, for Keras, or for TensorFlow. But if we want to release this package, it's not just a package, it's an entire process of learning process. So I think for myself or for my research group, we have unable to have done all the job. Industry level companies, if they're interested, they would like to engage. I would like them to engage and to release new package. And to be very honest, right now I use MATLAB with GPU, but without C++. To finish image and training with my proposed method, I need to take 170 days to get the result. So that is reason I don't know. I'm not sure what is the future, but if more people and more companies, industrial level application has been involved, definitely we will have much bright future.
So I noticed someone raised their hand. I forgot, maybe it was. Okay, Protein. Yes, please ask your question.
Hi, thank you for your talk. Hello? Hello?
Yeah, I can hear you.
Okay. Yeah, thank you for your talk. Just following up from that first question, are the echo state networks, are the recurrent networks in them able to be unrolled, and from those feed forward networks, are you able to get the arrows and the equations for the arrows and train like a reservoir computer in that manner?
Yeah, so echo state network is a little bit different because it's a recurrent network. So when for this kind of learning algorithms, the most important part is how to get the design output for each hidden layers. So I can share the here. So for example, here, the most important part in this one is how to get the design output P. Because we need to use design output P with the input X for updating weights. So in the echo network, because the state has been changed multiple times. So if we try to use this one, we will have multiple dynamic data. For example, we will have using bench size, right? Because we have big data sets, we have to separate the samples. And when the samples are time series data sets, how to separate samples. I'm not familiar with this, but I know definitely there are some algorithms in NLP area. The second one is that when the state's updated, the output of this one has been updated. When the output has been updated, how to define the arrow and how to use such arrow to get the design output of P. This is another process. But so that's this reason I don't know, I have no time to think about this one, but thank you for your guys' questions. So when we try to use these algorithms for echo state network, it is some problems, but I believe you can try. You can try to do this. For me, is that learning rate is very important. If you have some learning rate, then you can add the learning rate in this design output. Then maybe you can use the same equations to get a result.
Okay, thank you.
Thank you.
So I have another question. Do we have much, is there any kind of theory about, say, function classes that are actually learned in this way or kind of induced by this way of training? Because as you know, I mean, say if it, for some class of, say, neural networks, we know something about, say, the implicit regularization that is induced by SGD. Now I'm wondering whether there is similar type of theory
Yes.
for type of networks or not.
Yes. In this area right now, the theory is very, very limited. I think it's not because there's no theory, maybe because my background of knowledge and because I come from the computer engineering. So, and in this area, actually, there's limited research come from computer science. So if more computer science, especially from the pure mathematics, can involve in this area. So I can show you very important information is that when I have this idea, bidirectional ELM, so I found the performance is really good. So let me see here. So the performance is really good. So one reviewer in 10 years ago saying, can you prove these formulas? Can you give me the mathematical proof? I said, I can't do that. Then he suggests me to use VC dimension. He said, VC dimension is a tool. If you can use a VC dimension to prove these algorithms, then you build some fundamental cornerstone in the mathematical part. But based on my knowledge, I don't know how to prove. Even I try to do this job for years, but I still cannot finish the VC dimension improvement. So one of my students has tried to get some result, but I don't know. I'm not sure. So this is also, so for me, is that this area is brand new, it's interesting, but it's highly risky. If more computer science researchers could have interesting to join, to move into this area, to take a look why we have such result, I would be very appreciative, very thankful, and also one day maybe. So right now we are facing a lot of problems with GPU, because GPU is very expensive, and so if we can solve this problem in the future, if we can use CPU to train our network, this is totally another story.
Okay, thank you.
Thank you.
Is there any other question? It seems not. Okay, so thank you again for your great talk. It was very interesting, and let's join me in thanking the speaker.
Thank you for having me. Okay.
Thank you, everyone. I hope everyone has a good weekend.
Bye-bye. Have a good day.
Bye.